This talk should have been given by Patrick Richard. As you have seen this morning, I am not Patrick Richard. He decided not to come because he will go in Australia to hunt kangaroos. So it's something which is not so far from the other system. It's a setup where which is also confined between side walls. But here, contrary to what I showed this morning, the flow is at atop a heap, so it's a neoliberal base. This the work has been done by about the same guys as this morning. So it is an experiment which we began to work on it some time ago. In fact, it was a PhD subject of Nicolas Taberlet. So it's a flow atop a heap, and so the parameters we choose are the mass flow rate and the distance, the gap between the side walls, W, the width. And what we observe is a localized flow at the surface. So if we choose in the experiment, the parameter is the flux. If Q is fixed, if we wait a little, we observe SFD flows, and the nature of the flow depends on the flux we choose, we fix. In these flows, you have different parts. You have at the surface of the flow, you have a ballistic zone where the grains are mainly jumping. And you have a part here, it's a photograph which has been taken with a rather long, not so long, but time of exposure, so that the part which is flowing is in gray here. So the thickness of this part is H. And below, you have a quasi-static part with, on the angle of the surface, or the interface here, is named theta. And this angle, what is specific is that this angle depends on the flux Q. When Q increase, it's possible to increase the angle theta. So for large Q, you get flows on angles which can be very large, much larger than the angle of repose. It has been shown that these flows obey some kind of flow which relates the angle to the thickness of the flow divided by the width, the gap between the two side walls. And there are coefficients here. One of them is the effective friction coefficient which corresponds to mu of I, the friction between the flowing part and the static part. And the other coefficient corresponds to the friction between the flowing part and the walls. So there were experiments, but I will mostly speak of numerical simulations here. So these simulations have been made about in the same way that what I've shown this morning with linear spring dashpot model. So some people explained it before. I will go fast here. We took a friction coefficient of 0.5 in general. It will vary after, and a restitution coefficient of 0.88. So also at the beginning. And the simulations are made with about 50,000 grains in the case, mainly in the case where it's rather large with a width of 30 D. And when the width is smaller, the number of grains is smaller too. It's not necessary to take so many grains when the width is small. So we developed two kinds of simulations, a full system simulation and a simulation with periodic boundary condition in the direction of the flow. So this is generally more time consuming. So it is generally easier to do it this way. But we checked that it gives the same. Here the parameter you choose, the input parameter is the flow rate. And the system chooses himself the angle like in the experiment. In this case, in fact, we incline the periodic cell on not the periodic cell itself, but we incline the gravity. And it chooses, so the parameter is the angle of inclination of the gravity, and the system chooses itself the flow rate. But we check that it gives the same thing. Both give the same angle. The relation between the angle of the flow and the flow rate is the same in both conditions. So then we mainly use the periodic boundary conditions simulations. Here are typical results for, so you have different widths, 5D, 10D, 20D, 30D, and different angles. And you have here the packing fraction profile. So here it's the part at the surface where the grains are jumping, so the very low packing fraction. And here is the quasi-static part where you have high packing fraction, which is about 0.6. And you have a large variation of the packing fraction in the part which is flowing. So it's very different from what you get with a hard base. The second point is that it is possible to rescale all these curves by using only one length, characteristic length. So if you draw here the packing fraction divided by the maximum value, which is the same in any case, about 0.6. So on if you rescale by this characteristic length, all the curves collapse, all the profiles collapse. So it means that it is a characteristic of the flow. What is interesting is that this is the same scale than the scale which for the velocity. The velocity profiles first in 3D are like that. There is not a lot of shear. Here you have the boundaries, here, and here are the profiles. So according to the distance to the walls, and here it is the height. So it's faster at the surface, and so it's maybe easier here to look at it. It's not necessary to have a 3D representation as there is no shearing. So you have here different velocity profiles for different values of the width and of the angles. And if you plot by rescaling by the same length L nu, the same that for the packing fraction, the curves collapse except for the angles which are small, like 30 degrees, which corresponds to situations where you are nearly jammed. It begins only to flow. So the packing fraction and the velocity share the same characteristic length, and we can define the depth of the flowing layer as 2 times this characteristic length. If we look at the shear rate, they have all the same shear rates independently of theta. It depends only on W. If you look here at not independently of theta, but for angles which are large enough. So if we look at the variation with the angle, it increases the shear rate and then it saturates. And the value of the saturation depends on W. It varies as the square root of W, of the width. So there is a scaling of the shear rate with the width as the square root of W, which can then give us a scaling with the flux and so on. I will come back to this question at the end. The characteristic length varies with the width too. And if we draw the relation, so L nu, the ratio L nu over W for the different values of the angle, we have nearly linear relation, as it should, because it is the same. In fact, as L nu is related directly proportional to the thickness of the flow, it is the same relation than the one I mentioned before, this one. So H is 2 times L nu, so it is a linear relation between tangent theta and L nu that over W. It's exactly what we see here. So we recover in the simulations what had been observed in the experiment. So it allows to get these two effective friction coefficients. As I mentioned before, we only need to calculate the slope on the intercept. And we can look at the variation of these two parameters, these two friction coefficients, with the parameters of the simulations, for example, with the friction between grains and with the friction between the grains on the wall. So here in red, it is the internal friction, and in black, it is the friction with the wall. So you see that the variation of these frictions with the microscopic grain-grain friction coefficient is small, especially for the friction on the wall. But the dependency with the microscopic friction coefficient grain wall is much more important, especially mu W, which was what we could expect. So this friction is more important than the other one. This one is more important than this one. But what is funny is that even the internal friction coefficient, which is the equivalent of mu of I, depends on what happens on the walls. Means that local rheology is not so local because it depends on the boundary conditions, in fact, so slightly. We looked at the resultant sidewall friction coefficient. That means the shear stress on the sidewalls divided by the pressure on the sidewall. And so here it's for a given value of the width and different angles. You have here the variation of the friction, the local friction on the wall. So here it is the surface. Here it is in the depth, so in the quasi-static part. Here it's the part which is flowing. So what you see is that in the part which is flowing, it's nearly constant, and it's about the value of the microscopic coefficient of friction between the grain and the wall. When you go deeper inside the heap, it decreases. But nevertheless, when we look at the friction, at the motion of the grain, they are slipping. It means that each grain is slipping, so with the value of the microscopic, it saturates the friction, but globally it decreases. So there is a mechanism which allows that. I will show you just after. And the other point is that everything can be rescaled also here with the characteristic length. It depends on the same characteristic length than the packing fraction and so on. So why is it decreasing? In fact, it's due to here we can explain it easily, but what we have seen in the experiments, the grains which are deep inside the heap, they cannot move easily. They are in some kind of cages, like for glassy behavior. And they are only jumping inside the cage. And sometimes they have jumps, larger jumps, when the cage is deformed. So most of the time they have contribution which is in average 0 because they go everywhere. And so the average in all these directions gives 0, and only the jumps contribute to the macroscopic friction. And as the time they spend in the cage becomes larger when you go deeper, in fact, you have less and less jumps, so less and less contribution to the friction. So if I continue on the sidewall frictions, we can vary also the grain wall friction. We can see that in any case, it's always saturate in the flowing part to the value of this microscopic grain wall friction. And the effect of the grain-grain friction is very weak too. So it confirms what I said before. It's mainly the grain wall friction which is important. Now we can calculate the friction mu and the inertial number, and draw the packing fraction according to the inertial number and the friction according to the inertial number, what we see is that in the part where the inertial number is lower than about 0.5, all the curves are almost collapse for the different values of the angle. It's the same, it's true for the packing fraction and for the friction, but for in the other part, when you have a packing fraction which is low, or if you go in the part, so it is in the part where it's dilute, and here also, it doesn't follow anymore the viscoplastic rheology. And it's also, you have also strange things in the part, in the quasi-static part. So both in the quasi-static part and in the dilute part at the surface, it doesn't work. So we try with viscosity, as Michel said on Monday. It's possible to calculate the viscosity, and we draw it here. It's according to the depth. So we see that it's better, especially in the dilute part. It remains different in the quasi-static part, but it's possible to draw it in another way. I will show after. Here it's in log. And if we draw this viscosity according to the packing fraction, in this case, almost all the curve seems to be collapsed. So it seems to be better as a normalization. It remains things which doesn't work so well in the dilute part, but maybe we should also divide it by the square root of the temperature, as in the kinetic theory. So to finish about that, I will come back to the scaling, the question of that Michel Louge addressed on Monday. So in the simulations here, we can see that the scaling is that the flow rate per unit width behaves as the gap at the power 2.5. That's what we see here. Everything collapses. And Michel has shown on Monday that for the experiments on the same setup, the scaling is with the power 1.5, so it's not the same. We don't understand why. Everything is, when we compare the experiment and the simulation, everything looks similar, but these scalings are different. So it has even qualitative effects that as the shear rate in simulation behaves as the square root of the width, and in experiment, it will be the inverse of the square root of the width. So when you increase the width, one of them decreases and the other one increases. Okay, I will finish on this question.
Yes. Yes. I didn't understand how you measure mu I, the internal friction coefficient, or where.
It depends. In this case, no, before. Yeah. Yes, yeah. In this case, we measure it only by taking we draw a straight line, and you take the value of at the intercept. As it is, the relation gives you tangent theta equal mu I plus and so on. So it is the value of the intercept. As soon as you have the linear relation, you are able to get the intercept on the slope. So you get mu I and mu W. Okay?
Show the other graph. It's not tangent theta versus h over theta.
So you draw this line, and you get the value.
No, I don't think it's in that graph that you showed. It's h over w versus tangent theta. Or
but h is the same.
Oh, I see. I'm sorry. Okay.
It's only there is a factor 2. That's why.
Oh, thank you. Sorry about that.
In the case here, we calculate exactly with the stress tensor for the component of the stress tensor. So we calculate it everywhere.
Any other questions? Yes. What about second normal stress differences?
Sorry?
Second normal stress differences?
I have not there. When we calculate this, we see that it is isotropic in the flow,
Yeah.
but it becomes anisotropic in the dilute part. Or also, it depends on the stress component, but everything is the same in the flowing part. It's like hydrostatic pressure. But if you go in the upper part, in the dilute part, or in the quasi-static part, it becomes anisotropic.
Okay, with that, let's thank the speaker, all the speakers in this section.